Welcome to the wonderful world of physics. This is section 24 on fields of charge distributions. In the last section, we looked at the electric field, and we looked at the field produced from a single point charge. Now we're going to look at when there are many point charges or a distribution of point charges, and we'll see what the field is that comes from that. If there are many charges producing a field, we use what's known generally as the superposition principle, which means that the total electric field in the region is the sum of all the individual electric fields. So we can say it would be the vector field from point charge 1 plus the vector field from point charge 2, etc. And there might be 2 point charges, as you can see in the diagrams below, or there could be trillions of point charges. So if you look at the diagrams below, we have at the top diagram, we have 2 point charges. One of them is negative and the other one is negative, and they are equal charges. So what we have is these field lines that, remember that a field line, an electric field line, shows the direction that a positive test charge would get forced. And so, for example, let's say where my pointer is, here's a positive test charge, and it would be forced towards the negative charge on the left, but it's also got a little bit of a pull towards the charge on the right. Now the charge on the left has a stronger pull because it's closer, but there's still that little bit of a pull to the right, and so it doesn't go straight into the charge that's right below it, but it veers a little. The closer it gets to the charge on the left, then its comparative closeness between the one on the left and the one on the right is even more so, so it gets pulled more into the negative charge and it curves in. A positive test charge right in the middle has no vector. The electric field is 0 because right in the middle it's equally pulled towards the one on the left and the one on the right, and those two vectors cancel out. If you look at the diagram below, a positive and a negative charge, again they are equal and opposite charges. Let's consider a positive test charge right where my marker is. And you can see mostly it gets repelled by the positive. Actually, let's put it right here. It gets mostly repelled away, radial away from the positive. But the farther away it gets from the positive, it feels more of a pull towards the negative. So instead of going radially straight out from the positive, it starts to curve inward, and before long, it's feeling more of the pull towards that negative than the repulsion from the positive, and it gets pulled in there. So what you're looking at in these two pictures are the electric field from two equally charged, from two equal charges. The one on the top is actual equal signs, and the one below are equal charges or equal charge magnitudes, but opposite signs. Well, these two are just examples, the simplest examples of multiple charges, so equal charges, but either equal or opposite signs. Now we're going to get into, in this section, when there are many, many more charges. So we look, for example, actually in this example it's still just 2, but we'll get into multiple charges soon. Example 24. The field between 2 protons. It says 2 protons are 3.6 nanometers apart. Find the electric field at a point between them 1.2 nanometers from one of the protons. Then find the force on the electron at this point. All right, so you look at the picture. Before we get into the math, let's just think conceptually. Let's draw a picture. We have the positive and the positive, and there's the point that we're looking. It's closer to the one on the left, so the electric field from the one on the left is going to be stronger than from the one on the right. And you can see the directions I've drawn them. Remember, electric field, when you're thinking what directions to draw it, it's the direction that a positive test charge would go. And so it will be repelled away from the one on the left, it will also be repelled away from the one on the right. So I've drawn those directions accordingly. And so ultimately, because the one on the left pointing to the right is stronger than the one pointing to the left, the one on the left is going to overwhelm the one on the right. And so ultimately this entire electric field we know should be pointing more to the right. Well, let's do the math now. The electric field is the electric field from charge 1, I'll call that's the one on the left, plus the electric field vector from charge 2. Well, the one from charge 1 is K, that Coulomb constant, times the charge of 1. Now it's a proton, so we give it that elementary charge E, divided by the distance from 1, we'll call that R1 squared, I hat, pointing to the right. And then plus, from charge 2, Ke over R2 squared, and since it points to the left, we'll call it negative I hat. And now we just fill in all those quantities. For K, I've just done two significant figures, 9.0 times 10 to the 9th. If you want to be more accurate, you can do 8.9876, real easy to remember, 8.9876 times 10 to the 9th. But here, two significant figures will do. For the charge, I've written 1.6. I was just meaning to save some space there. It's good to use the full four significant figures, 1.602. But here we go. You plug those values in. You have the distances, nanometers is times 10 to the negative 9. And then you should end up with 1 times 10 to the 9th I hat minus 0.25 times 10 to the 9th I hat. And I hope that you do these along with me in your calculator to make sure that you get the same results I've gotten. So in the end, we get 0.750 times 10 to the 9th newtons per coulomb I hat. And since it's positive, that means it points to the right, which is what we expected up here. The next question asks, what will an electron there feel? What force will it feel? And so remember that the force that a certain particle feels is just that particle's charge times the electric field vector. And the charge on an electron is negative E, 1.602 times 10 to the negative 19 coulombs, times the electric field vector, which you see right where my marker is. And so it becomes negative, meaning pointing to the left, 1.2 times 10 to the negative 10 newtons I hat, which means an electron overall will be forced to the left because the electric field goes to the right. Let's talk about something called a dipole. An electric dipole is 2-point charges of equal magnitude and opposite signs. And we see this often in nature, and one common example is a molecule like water. You can see my hand-drawn diagram here. A water molecule is an oxygen and 2 hydrogens, and by the way, it's arranged with the electrons. It's more positive on the hydrogen sides than on the oxygen. So we can think of a water molecule as a dipole being positive on one side and negative on the other side. Let's look at this example in the book, example 25, modeling a molecule. It says a molecule may be modeled approximately as a positive charge Q at x equals a, and a negative charge negative q at x equals negative a. And just to be clear, it's not just saying any random, all molecules can be modeled this way. It's saying a particular model that the author has in mind can be modeled this way. Evaluate the electric field on the y-axis and find an approximate expression valid at large distances, meaning y is much, much greater than a. All right, so let's draw this out. We have our x-axis, negative and positive. And the charges that are given, it says negative q. Now, I haven't written out the q's there, but we have negative and positive. And those distances, okay, good. The positions are negative a and positive a. Now, if we think about the field lines, and I want to think along the y-axis because that's what the question says to do, evaluate the electric field on the y-axis. From the charge on the left, it's a negative charge. And so its electric field vector goes straight radially into it. So this I've written as the electric field vector as a result of the negative charge. Now, as a result of the positive charge, there's an electric field vector going up and to the left, going radially away from it. If you add these two vectors together using the superposition principle, then their y's, the one goes positive y, the other goes negative y. Those are equal and opposite. They cancel out. And the net electric field is just going to be strictly in the negative x direction. So due to symmetry, the y components cancel, and that is because of the symmetry of the problem and the equal and opposite charges. And so we're really going to concern ourselves with evaluating just the x direction. Let's evaluate the magnitude first of E negative, the E negative magnitude, and that is k times negative q times or divided by r squared. And that is just generally what you learned in the previous section, the previous lecture, is the electric field from a point charge. It's k times the charge that's causing that electric field divided by your distance squared, which I've called r. All right. So I brought that up to the next page. We only need its x component. And so with a little bit of similar triangles here, we have there is that the electric field vector, and there's the distance r. And on my previous picture, here was the charge, and here was the y-axis. And so with similar triangles, if I want to know what is the x component of that electric field, similar triangles say that the x component of E divided by E is equal to A over R. And that means that the x component of E is E times A over R. So now I can say that the x component of the negative from E is k times negative q over r squared, and then times A over R. So now bring that here, the total electric field, because remember there are two charges, there's the negative and the positive. So using the superposition principle, the total electric field, and we're only looking at the x component because the y's canceled out, is negative kq over r squared times A over R I hat, plus negative kq over r squared A over R I hat, because they were, if you look back at the picture, they were both pointing in the same direction and they were equal to each other. So the first one we can say is from the negative, the second is from the positive. Adding those together, we get that the total electric field is negative 2 qka over r cubed I hat. Now r is just a quantity that we use to make the picture. Let's put this in terms of A and Y. So A is the original, the distance given between the y-axis and those charges, and Y gets to the distance because the question was asking to evaluate the electric field on the y-axis, and that's going to refer to how far away it is, so that's going to be what y is. So using Pythagorean theorem, I've turned r into a squared plus y squared, or I should say r squared is a squared plus y squared, and so r cubed is a squared plus y squared to the 3/2 power. So when you work it all out, this is it. This is the electric field as a function of q, a, and y. Notice that it is negative I hat. It points to the left completely, and to the left meaning in the direction of the negative charge. There it is again, negative 2 kqa over a squared plus y squared to the 3/2 power. Now, the question then says, find an approximate expression valid at large distances, meaning far away where y is much, much greater than a, and we're no longer looking microscopically at that there's a positive and a negative next to each other. What happens when we get very far away? Well, if y is much greater than a, then in the denominator we can neglect a squared, turning that denominator into y squared to the 3/2 power, which becomes y cubed. So the electric field then is roughly 2kqa over y cubed I hat. And it falls off, you'll notice, as 1 over y cubed, so it falls off rapidly. And this, in fact, is what we get if you're not too far away, then where I've put my green star, where my marker is right here, then yes, indeed, it does point to the left. Now, if you zoom out so that y is much, much greater than a, and this is what I've tried to draw on here, although it's kind of a cramped picture. If you zoom out, then you think about it, you're dealing with a positive and a negative charge that are together, but you're so far away from them that essentially they negate each other and it's just zero charge. So that's the idea that the electric field falls off as 1 over y cubed. You get significantly far away, then you just have zero charge. Zero net charge is felt at a distance. At large distances, the electric field is approximately QA, the charge times the distance between them. And this brings up a new physical concept, something that comes up often in electromagnetic theory, electric dipole moment. So we use the letter P when we're talking about a dipole. At large distances, a dipole's electric properties are characterized completely by its electric dipole moment P. And it's defined as the product of the charge Q and the separation D between the two charges making up the dipole. Now, in the previous example, we used A because the example said A is the distance between the charge and the middle of the dipole. So really D here now, the separation, which is a more useful term here. This separation D is just 2A. So relating to the previous example, we can also say the dipole is 2A times Q. So the electric field is negative K times the dipole divided by y cubed I hat. And so here you see the picture. We have the negative on one side, the positive on one side. If we're evaluating the electric field up here, then this is the formula we're going to use, that the electric field is negative K times the dipole over y cubed. Now on the dipole axis, let's say we have the negative and positive. Let's think about where my green star is right there, or I'll just put the marker there. What is the electric field? Well, it's more strongly feeling the positive than the negative, and the electric field actually comes out to be 2 kp over x cubed I hat. Now, what if we have a continuous charge distribution? We'll now consider a charge distributed over a region, perhaps a surface of a metal plate or a volume of a material. Now we're looking at many, many, many charges. So you think superposition principle, let's just take comparable to a mole of particles, 10 to the 23rd. That's going to be a lot of calculations. It's too much to compute. And so we need a way around it. And usually when we get to very, very big quantities of things, we get into calculus. So here we have calculus to the rescue. If a charge is distributed over a volume, we're going to use a quantity called the volume charge density. And we use the Greek letter rho for that, kind of like mass over volume is density, what we learned last semester. Well, volume charge density, we also use rho, and it's coulombs. Instead of kilograms, it's coulombs per meter cubed. how much charge is spread out over a volume. Or if the charge is distributed over a surface, we'll use surface charge density. And for surface, we use the Greek letter sigma, and it's coulombs per meter squared. If the charge is distributed over a line, and you can see my diagram down below, many charges over a line, we'll use line charge density, and we'll use lambda for that, coulombs per meter. So remember the superposition principle, that the net electric field is the sum of all the little electric fields from all the different charges. What we're going to do is divide the charged region into tiny elements dq of charge. Each little dq element produces a tiny field dE given by, and this is the electric field from a point charge equation, but we've made, instead of E's and Q's, we've made dE and dQ. So dE is k dQ over r squared, and since it's a vector, we'll throw in the r hat. Then we're going to take the vector sum over all the little electric field elements dE. So here's what it's going to look like. The electric field is the integral of dE equals the integral of k dq over r squared r hat. The example we'll use is example 26, the field of a charged ring. It says a ring of radius a carries a charge q, capital Q, distributed evenly over the ring. Find an expression for the electric field at any point on the axis of the ring. All right. So you see the picture that I've drawn. Here's our ring with a radius a. It's got a charge q distributed evenly along it. And somewhere along the x-axis, along the axis of the ring, we want to know what is the electric field. You can guess that at great distances, imagine if you zoom far away from this ring, so far away that you can't even see that it's a ring, it just becomes a point. And so you can guess that at a very far distance, it's going to act like a point charge. Electric field is going to be kq over x squared, going to the right, assuming that's a positive charge on it. You can also guess that in the middle of the ring, where x equals 0, right where my pointer is, because it's right in the middle of the charges, they're all going to cancel each other out. Kind of like when we had, at the beginning of this section, two positive charges right in the middle, they all canceled out. So you can guess maybe that the electric field is going to be equal to 0, right in the middle, at x equals 0. So with those guesses, let's apply the math and see what happens. We're going to let the x-axis be along the ring's axis and x equals 0 be at the center of the ring. Recognize that all of the electric field in the y direction vectors will cancel from opposite sized charge elements. Meaning, you think right here where my pointer is, there are charges above it and there are charges below it. And so the charges above it are going to have an electric field pointing downward. The charges below it are going to have an electric field pointing upward. And since it's all symmetric, those are totally going to cancel each other out. All that's going to be left is the x component. So electric field is going to be completely in the x direction. We only care about the x components of the vectors. Look at this picture down below. Here we have a radius of a. We're trying to evaluate at the distance x. Now, what is going to be useful for our equations, even though we want it in terms of x, we're going to think of these electric fields in terms of the distance from a charge element, and that is r. And then there's the electric field. So as you look at this triangle, the x component of dE is going to be dE times cosine theta, basic trigonometry there, which is k dq over r squared times cosine theta. Now cosine theta is, just from basic trigonometry, x over r. So let's replace that cosine theta with x over r. We have k dq over r squared x over r. And then that becomes, let's get rid of the r, because r squared is x squared plus a squared. So that becomes dEx is kx dq over x squared plus a squared to the 3/2. Now what we're going to do is integrate over the entire ring. So the electric field is the integral over the ring of dEx, which is the integral over the ring of, and we're going to plug this part in, kx dq over x squared plus a squared to the 3/2 power. For a fixed point P along the x-axis, x will be constant around the ring, which means the x can get thrown out to the left. This is where we take the things in the integral, the quantities, anything that's constant, throw it out to the left. We factor it outside of the integral. X is going to be constant for all the different points on the ring. And everything except the dq in this expression gets factored out to the left of the integral. So very conveniently, we have kx over x squared plus a squared to the 3/2 power all put to the outside. All we're left with in the integral is the integral over the ring of dq. Well, that's a very easy integral to take. That is just the charge of the ring. So we make it capital Q. And so there's the expression for the electric field, K times qx over x squared plus a squared to the 3/2 power, and the direction is in the positive x direction away from the ring. And now we can test the initial guess. We said that for x much, much greater than a, it should act like a point charge. And so when you neglect a and make that denominator just be x cubed, it'll divide out with one of the x's. And there you go, kq over x squared, and that is what a point charge electric field looks like. Let's now do a problem in the back of the chapter. And as I'm in the second edition of Volume 2, this is problem number 55. It says a thin rod lies on the x-axis between x equals 0 and x equals L, and there's the picture you can see I've drawn, and carries total charge Q distributed uniformly over its length. Show that the electric field strength for x greater than L is given by E equals KQ over x times x minus L. All right, so we're given the result. We have to just come to that conclusion. So here's how we evaluate this problem. First, we draw a picture, and we want to know for x greater than L. That just means somewhere beyond the rod itself. We're going to establish the R that we're going to use is the distance from any charge element that we're going to evaluate to the given point. We'll start with E equals the integral of dE. And we know that dE from previous in this lesson is k dq over r squared. And that actually goes back to when we first learned about the electric field from a point charge. So k over r squared dq. Now, we're going to set up a ratio here. The ratio is that the charge element as a portion of the entire charge is equal to dr, and think of dr as the length of the charge element over the length of the rod. So dq over q equals dr over L. And then we can say dq is q over L times dr. The reason we're doing this is at the moment our integral is integrating over dq. And usually we don't want to be in a situation where we're integrating over charge, just like sometimes last semester. We didn't want to be in a situation integrating over mass. We prefer to integrate over space or time. So this allows us to integrate over space, dr instead of dq. So I make that substitution, and now we have k over r squared ql dr. Notice I've put in the limits of integration. We're thinking about what happens to r, because we're integrating over dr. So r, the distance from our point to the charge element, is going to be everything from x, and I've just arbitrarily made x from the 0 point to our point, so that's from x, actually it's the high end, and the low end distance is x minus L, which is this distance I'm covering with my pointer. So we're integrating from x minus L all the way to x. All right, now we just do the integral. Take the things that are constant, factor them out to the left, so kq over L, and we're left integrating with r to the negative 2 dr. That becomes negative 1 over r. I've thrown the negative sign to the left, and take that integration through, and here you can see I've plugged in 1 over x minus 1 over x minus L. I have now distributed the negative sign into that negative, which essentially I've reversed the order. Now it's 1 over x minus L minus 1 over x. I've taken it through the algebra, finding a common denominator between those two fractions. And in the end, I've simplified it to be kq over x minus L. And that is what the problem was asking us to show. Notice that when x is much larger than L, then that x minus L term just becomes x, as if L is just insignificant, so it becomes x, and that leaves us with the electric field being kq over x squared. What that means is this is a rod, but if we get far enough away from it, then essentially to us it's acting like a point charge. Let's look at example 27. Example 27 says, a long straight electric power line coincides with the x-axis and carries a uniform line charge density lambda, which is in coulombs per meter. Find the electric field on the y-axis using the approximation that the wire is infinitely long. Okay, so the approximation the wire is infinitely long, and you might think, well, we don't really have infinitely long wires. That is true, but if you have a 1 meter long wire and you're evaluating the electric field a millimeter away or even a centimeter away, then the length of the wire is effectively infinite compared to how far away from the wire you are. So it's actually a good thing to be able to do, a good useful thing. I've drawn a picture here and I want to know what is the electric field. And there's the electric field. Here's dq, assuming it to be a positive charge, and it is pushing away to the right. And there's a y component of it. Now, for every dq on the left, there's a dq on the right, and pushing away that way. So I hope you can see that, even though I haven't drawn it, that all of the x components of the electric field are all going to cancel. Again, you can think there's a dq right where my pointer is, and it's pointing up and to the left. It's going to cancel with the dq that I've drawn. All of the x components are going to cancel, and because it's infinitely to the left and infinitely to the right, and all we're concerned with is the y component. That is the electric field. I have dE equals k dq over r squared. That's basic from a point charge. The y component is, using some basic trigonometry, is k dq over r squared times cosine theta. That's the y component. And if we substitute cosine theta is y over r, then we can say that the y component of that, the dE sub y, is k dq times y over r, and then over r squared. So it's k dq y over r cubed. Now we're also going to use that we really don't care about r. What we care about is y and x. So we're going to use Pythagorean theorem that r is square root of x squared plus y squared. And so in this expression where my marker is with the r cubed on the bottom, we're going to turn that to x squared plus y squared to the 3/2 power. And now we're going to integrate that expression. The electric field is the integral of all these little electric field elements. So we have integrating from negative infinity to positive infinity, k lambda y over x squared plus y squared to the 3/2 power dx. Let's take the constants k, lambda, and y, factor them to the left, and we're left with this integral. uh, integrating dx over x squared plus y squared to the 3/2 power. Here is an integral that you probably don't know, and this is where a good table of integrals is useful. So a good table of integrals, a decent one is in the back of your book, but I recommend, particularly if you're going on to further physics or engineering classes, that you find yourself a good table of integrals. And so we look up in a table of integrals and we find that this is it. Integrating it becomes x over y squared, square root of x squared plus y squared. Again, that's not an integral that you're expected to have memorized. It's just one we look up. And when we plug in for x being infinity and negative infinity, we get 1 over y squared minus negative 1 over y squared. And it comes out to be 2k lambda over y. And again, going from this line with it integrated to making x infinity and negative infinity, be sure to go through it yourself and convince yourself that, yes, actually that does work. And if not, ask me in class. But you should get 2k lambda over y. And this works as long as the length of the wire is much, much greater than y. So again, it doesn't have to be an infinitely long wire. It just has to be much, much, much longer than the distance from the wire that we're evaluating. Now, what if it is a line of length L? Instead of infinite length, well, let's assume that we're taking a point that's perpendicular from the center. So now instead of an infinite length, it just extends out negative h in one direction and h in the other direction. And I've taken you through, done the same integral, and we're, as you follow through the work that I've done, plugging in for the limits of integration, negative L over 2 plus h, negative L over 2 minus h, eventually we get, as you follow through that work, 2lk lambda over y squared of L squared plus 4y squared. And one thing we can think about is, does it approximate a point charge if we get a very large distance from L, meaning y is much, much greater than L? Is it going to look like kq over r squared? Well, let's think Q, first of all, is the length times the length charge length density. So Q is L lambda. We're going to take in this expression L lambda, replace it with Q. And as you take the limit as L approaches 0, as L gets very, very small, then yeah, it eventually comes out to be KQ over Y squared. So this line, as you get very far away from it, we're no longer talking about an infinitely long line, so a finite length line. As you get very, very far away from it, it does start to look like a point charge. Let's look at a practical example of this. We just found in the last example that if we take a line of some finite length and we get some distance away from it, that the electric field is 2 times the length times k times the line charge density over y squared of L squared plus 4y squared, where y is our distance from the line perpendicular to its center. Or we can simplify that and say we can put length times line charge density together, and that becomes the charge distributed on the line. And let's put some actual numbers into this. Let's say that the charge distributed over the line is 1 nanocoulomb. The length of the line is 3 centimeters, so a little over an inch. And we are at a distance 3 meters away from it, so 300 centimeters. Length of 3 centimeters, distance is 300 centimeters. And I want to explore if we've got, and I want you to imagine that, picture that. So 3 centimeters long a line, pretty short line, and we're 3 meters away. That could be across the room. And I want you to think at that distance, we might be able to consider it a point charge because it's a lot easier. The equation for the electric field from a point charge is just a lot easier. and I want to explore, can we consider it a point charge? And how much accuracy do we lose? Is it reasonable to just consider it a point charge and ignore the fact that it's a line? So what I want to do is compare the electric field given by this equation to the electric field estimate for just pretend that it's a point charge. Well, when you plug in the values, the electric field using this expression, using those numbers, comes out to be 0.99865 newtons per coulomb. If we just ignore this expression and consider it as a point that has a charge of 1 nanocoulomb, and we are 3 meters from that point, we get 0.99866 repeating newtons per coulomb. So it's very close, which means as long as you're fine with the fourth significant figure, it doesn't matter whether you treat it as a line or a point, and it's just easier to treat it as a point particle. Now, let's say that y is equal to r. That's what we would do mathematically if we're comparing between this line. Remember that when we thought of it as a line in the expression up above, y was our distance from the line. And when we thought of it as a point charge, r is the distance from it. So mathematically, we're going to just say y is equal r. So let's take a ratio of the electric field, the true electric field, using the line charge equation, over our estimated electric field for a point charge, setting up that ratio. So it becomes 2kq. I'm using this equation here, but again, I'm turning all the y's into r's. So 2kq over r, formerly y, square root of L squared plus 4r squared, times r squared over kq. Again, that's divided by kq over r squared, but I'm multiplying and flipping it. And when we simplify, the kq's divide out and a power of r divides out, we get 2r over square root of L squared plus 4r squared. So what I'm doing here is I'm looking for, given a certain distance from our line, we're getting a large distance away, how does the accuracy change? What is the ratio of the true value of the electric field to our estimated value with a point charge? Now, if r is 10 times the length of the line, and remember up here, r, the distance, here it was called y, but the distance was 100 times the length of the line. If r is only 10 times the length of the line, then that ratio becomes, and I plug in the values, and I get 0.9988, which means that we don't have to be that far away from that line. Imagine it's a 3 centimeter long line. If we are just 30 centimeters away, about a foot away from that nearly a bit more than an inch long line, then the ratio between the real electric field and the point charge estimate is 99.88%. That's very close, which means that we don't even have to be really far away in order to use the point charge estimate. If we are only 5 times that distance away, meaning if it's the line is 3 centimeters long and we're only 50 centimeters away, then that ratio becomes 0.995, which means that even for that short distance away, 5 times the length of the line, we can get away, depending on how precise we need to be. If we need to figure out what the electric field is, we can just use the simpler point charge estimate, treat it as a point, and we're going to lose some accuracy, but we're still going to be 99.5% accurate. That is the end of section 24, Fields of Charge Distributions. Have a great day.